Hello. In the last lesson, we looked at deriving the area formulas for both, what was it, parallelograms and triangles. In this lesson, we're going to look at deriving the formulas for the areas of trapezoids, rhombi, and kites. So we're going to start with the trapezoid first. The trapezoid is a quadrilateral, so a four-sided polygon that has exactly one pair of parallel sides. If it had two pairs, we'd call it a parallelogram. So a trapezoid is a quadrilateral that has only one pair of parallel sides. The area of a trapezoid we're going to do is we're going to work with kind of an example case and use like a picture proof again. So consider the following trapezoid and the top and the bottom of the parallel sides. What I'm going to do is notice that, hey, if I copied the trapezoid and then flipped its friend upside down and put alongside it, it's going to make a parallelogram. And I know how to find the area of the parallelogram, so let's write what the total bases would be. Well, notice that this right here would be 5. This is 7. If I flip it upside down and then put it next to each other, this would be 7 and this would be 5. And then this whole height would be 4. So what would the area of the entire parallelogram be here? Well, the area of the parallelogram is always base times height, and the entire base is 7 plus 5, so 7 plus 5, and then I multiply by the height, 4. So the area of the entire parallelogram is 7 plus 5 times 4. The trapezoid is half of the parallelogram, so the area of the trapezoid must be 1/2 of 7 plus 5 times 4, and that is where we get the formula for the area of a trapezoid. A trapezoid is always half of a parallelogram that would be made by a duplicate of the trapezoid, and so the area of a trapezoid is always 1/2 the sum of the bases, because I would need the sum of the bases to make the parallelogram because it gets flipped upside down, so I'd have base 1 plus base 2 here, or base 2 plus base 1. That would be the entire base of the parallelogram times the height, and then the trapezoid is 1/2 of that. So the area of a trapezoid is 1/2 the sum of the bases times the height. The sum of the bases, because that would be the entire base of the entire parallelogram. You see the book writes it as 1/2 height. It's the same as if I wrote the 1/2 and then did the base sum first. The order doesn't matter because this is just multiplication of 1, 2, 3 things. I can move the order of those multiplication of those 3 things around and it's the same. So that's where we get the area formula for a trapezoid. We're going to use it now. So the windshield on most cars can be approximated by a trapezoid. Find what the area of the windshield would be. How much glass would it take? The area of a trapezoid, which is our approximation here, is 1/2 the sum of the bases, b1 plus b2, times the height. A good question would be, does it matter which one I call b1 and b2? It absolutely does not. So area is 1/2, maybe 85 plus 72 times the height of 38. Area equals 1/2. 85 plus 72 is 157 times 38. So I multiply all of that out, and I end up getting area is equal to 2,983. My units are inches squared. Area is square units. So there's the first question. Second question, in order to put the glass on, you need to put the edging around the outside. How much edging would it take in order to seal the glass to the frame? So it's a perimeter question. I know the 2 bases, but I don't know the slant distance. I know the perpendicular height, but I don't know the slant height. So how am I going to get to the slant height? Well, let's draw this out some more. Here is the picture. I know that this is 38 right here. I'm trying to get this, let's call it C, because it's going to be hypotenuse sort of a right triangle. I know that from here to there is 72, so this must be 72. From right here to right here is 72, and I also know the entire thing here is 85. So how can I figure out what these are? Well, they have to be what remains. 72 minus, or 85 minus 72 is 13, which means each of these need to be 6.5. That has to be 6.5, and that has to be 6.5, so that the entire bottom would be 85. Now I have a right triangle. I have a squared plus b squared equals c squared. So I have 6.5 squared plus 38 squared equals c squared. Pythagorean theorem, because that's a right triangle. 6.5 squared plus 38 squared is 1486.25. Then I take the square root, and I would have two answers, but because this is a real application, I only take the positive, 38.55. My units are inches, but I need to do the whole entire perimeter anyway, so C is 38.55. So if I add up all the way around, the whole entire perimeter is two 38.55s, because there's two sides, plus 72 plus 85. So 38.55 times 2 plus 72 plus 85. It's 234.1 inches. Perimeter is one-dimensional, just a length. That's how you would find the perimeter of the trapezoid. Going to ask you to try one. Here's a picture of kind of a unique pool. An owner wants to buy a tarp for the pool. Each side has a length of 15 feet. From one side to the other side is 26 feet. So from one flat side to the other flat side is 26. And the distance from one vertex to the opposite vertex is 30 feet. That's actually true for any regular, this is a hexagon. The reason why is because if you drew the triangles in here, so if I actually drew this all the way across, look, if this is 15 from here to here, this has to be 15 and this has to be 15. It's always going to be double. So if you have a regular hexagon, it's just a geometric property that the diagonal distance from point to point is always twice the side length. So that's just a property I'm sharing with you. You have all the dimensions you need in order to find, for me, what the total area would be, because this hexagon is really two trapezoids. So pause the video now, unpause it when you want to come back and see what the answer is. Okay, welcome back. Here we go. Let's just do one of these, right? The area of one of these guys is 1/2 the sum of the bases. 15 plus 30 is 45. The height of just one of these is 13. And if I find the area of one of them, what's that going to end up being? 45 times 13. And then if I take half of that, I get the area of one of these is 292.5. But then I double it because there's two of them. And when I double it, I will see that the total amount of square feet of tarping that I would need is 585 square feet. So there you go. Some of you might realize I could have just made the two trapezoids into a parallelogram and just done it with a parallelogram that has a base of 45 and a height of 13. And 45 times 13 would give you the 585. Last two shapes we have for this section are what are called a rhombus and a kite. The definitions are not in the notes, just for reference. A rhombus is any parallelogram that has equal sides. So a square is a rhombus, but a rhombus is not exactly going to be guaranteed to be a square, because a square has to have 90-degree angles as well. So there you go. I think I said that right. Rhombus, any parallelogram with equal sides. So yes, a square is a rhombus, but a rhombus is not guaranteed to be a square. A kite. A kite is a quadrilateral whose four sides can be grouped into two pairs of equal length sides that are adjacent to each other. So it's a four-sided figure where the adjacent sides are of equal length. So a figure that looks like that, what we call a kite. The area for a rhombus or a kite has an interesting formula that we're going to derive, but the formula for the area actually turns out to be 1/2 the product of the diagonals. If I multiply the diagonals and I take half of that, it turns out that is actually going to be the area of the rhombus or the kite. It works for both. Our textbook just shares the following and doesn't prove why this is true, so I'm going to share the proof with you, because next year in geometry you're going to prove a ton of different things. So here's the proof for that, because that seems like a really strange formula. Here's the proof for it. So the area of the kite has to be equal to, so here's the entire kite, has to be equal to the area of triangle ABD plus the area of triangle BCD. Let's use some colors so you can see what I'm talking about. Area of triangle ABD is the top one, and then the bottom one is BCD. So the entire kite has to be the area of the red triangle plus the blue triangle. I think you would agree with me that that makes sense. How do I find the area of the red triangle? Well, the area of the red triangle is 1/2 its base, which is BD, times its height, which is AE. And then the area of the blue triangle is 1/2 its base, which is also BD, times its height, which is EC. And so 1/2 base times height for each of them. You'll notice they have something in common. They both have a BD in them. So I can factor that BD out. And I can actually factor the half. They do both have a half. So they both have a half and they both have a BD. So I can factor out a 1/2 BD. So if I divide out a 1/2 BD from the first statement, what am I left with? AE. If I factor out a 1/2 BD from the second statement, I have EC. We're just doing the distributive property backwards. We did this a lot when we were doing quadratics. This is greatest common factor factoring. 1/2 BD and then the sum of AE plus EC. But now look, note that BD is actually diagonal 1. The distance from here to here, that is diagonal 1. Doesn't matter which one you call diagonal 1 and diagonal 2, but just note BD is one of the diagonals. And look at what the other one is. Purple, this one here. AE, which is here to here, plus EC. If I add those together, that is the other diagonal. So that's the other diagonal. So I have 1/2 of the green diagonal times the purple diagonal, and that is exactly what we were trying to show. It's 1/2 green diagonal times purple diagonal. So the area of the kite we just proved is 1/2 the product of the diagonals, just using a few steps and geometry. That's what you'll focus on a lot next year, is proving formulas. So here's an example. Once you've proved it, you can use it always and forever. Here's an example. Find the area of the kite that is 18 inches in one diagonal and 30 inches in the other diagonal. So the area is 1/2 the product of the diagonals. So 1/2 18 times 30. 1/2 times 18 is 9. 9 times 30 is going to be 270. My units are inches and area is square, so inches squared. One more, then I'm going to have you try. It says one diagonal of a 240-inch kite is twice as long as the other diagonal. What are the dimensions? So let's write out what the area of a kite again is. It's 1/2 diagonal 1 times diagonal 2. Let's write down what we know. We know the area is 240, so let's put that in. 240 is equal to 1/2. And then it says that one of the diagonals is twice as long as the other. So let's say that diagonal 1 is that really long one. If it's twice as long as D2, then diagonal 1 is actually equal to 2 D2s. So this would be 2 D2s times D2. Then I just multiply. 1/2 times 2, well, that's just 1, so I get D2 squared. And then how do I undo the square? I take a square root of both sides. The square root of 240 is going to be 15.49, approximately 15.5. That's diagonal 2, and diagonal 1 is twice as long, so I double it. If I double it, it's pretty much 31, 30.98. Did it give me units? Inches. So this is inches, that is inches. So pretty much 15.5 and 31. Last one. Here, I give you one of the diagonals, and I'm asking you what is x's length going to be if the total area of the kite is 92 inches squared. Pause the video now and unpause it once you've had a chance to try. Okay, welcome back. The answer is 4.2, and I bet some of you are surprised. The reason why is you probably didn't look close enough at the question. It asked for x, which is half of the other diagonal. I bet that you found that the other diagonal was 8.4, but you forgot to notice that x was half of that other diagonal, and so x is going to be 4.2. So make sure that you read the entire question and realize what it's asking. Thank you very much. Have a good day.